Good afternoon, everyone, and welcome to today's GOBLIN Working Group 1 Task 1.3 talk. I'm Puyu, co-lead of the Task 1.3, Integration and Interlinking of Knowledge Graphs. And today it's my pleasure to introduce our speaker, Enrico Daga from the Open University. Enrico Daga is a senior research fellow working in the knowledge engineering and the semantic web, and at the intersection of data integration, knowledge graphs, and data management. He is the co-creator of SPARQL Anything, a framework that lets any data format be queried as if it were RDF through the Façade pattern. And he co-chairs the W3C Data Façades community group. He has extensive experience with knowledge graph construction and its application across numerous domains, including cultural heritage, smart cities, teaching and learning, and social science. So welcome, Enrico, and you have the floor. Thank you so much.
Thank you so much for you and Eleni for the invitation and for giving me the opportunity to speak here at the GOBLIN talk. So the title of my talk is on Behind the Façades, so that attempt to do a 5-year recap of the work done around Façades and SPARQL Anything and whatever we have done in this area. And I hope this is going to be of some interest to you, and very much looking forward to the discussion. So let's see if I can move these slides. So knowledge graph construction. Clearly, I don't need to make this motivation for you, but just to set the scene. Clearly, data integration is the main dominant use case for knowledge graphs. And clearly what we know that we want to build knowledge graphs and fueling our ontology with data. And data, unfortunately, in most of the cases is not managed. Its life cycle doesn't happen natively in RDF, but more often RDF is a way to integrate and repurpose pre-existing data. So the main reference is data integration theory. Now, data integration theory essentially abstracts the data integration in a way to get a source schema. You have a global schema, that's the target representation that you want, and you have a mapping work that essentially establishes relationships between the source and the target. However, this abstraction leaves out syntax. So essentially assumes that the encoding of the data is either homogeneous, so it's the same format, the same meta model, or simply it is not important to the theory itself, which is both things are true in the sense that most of the integration research has been done in relational databases. And from the theoretical perspective, the encoding of the mapping is not probably the most important thing. But this has the fallback in the way research and practices on knowledge graph construction have been tackled in the last few 20 years. Okay, so what we did originally is to kind of look a bit with fresh eyes to the work on knowledge graph construction. So what do we do when we construct knowledge graphs? So essentially, we look at the input, we do some kind of observations, we have our own desired output, we do some design work, we run it, and then we evaluate, compare, and we do this in iteration, okay, many different times. In reality, when we design, from our perspective, we are doing two different things at once. One is we map the format. So we have like a CSV as input and an RDF graph as output, but also we project semantics. So we do what we call remodeling. So we do our reasoning on what is the meaning of the symbols in the source format. And we kind of do some operations so that we can project these semantics in the output. So looking into this, we thought, okay, in the case of knowledge graph construction, which is a special case of data integration, these two things cannot be fully automated. Okay, you don't know like what the ontology is, what is the use case. So you need to leave some kind of decision to the user, but there is something that you can clearly assume that what they want is RDF. So the idea is we can tackle the re-engineering step once and for all, then we can leave to the users to map a knowledge graph as input to a knowledge graph as a output. So how do we do that? So then we just don't try to reinvent the wheel. We look at this problem in object-oriented software engineering, which is a space where this problem came out so many times. And we look at the facade pattern. So the facade is a simple idea. You have a simplified abstraction over a collection of diverse objects that behave in a similar way. Okay, so from our perspective, you say, okay, we have a lot of data objects. We have CSVs, JSON files, XML files, Markdown files, BibTeX files, and whatever we want to think of. But inherently, we think that they may behave in a similar way structurally. Okay, and then the question is, how do we represent this facade in RDF? If we can have an RDF facade, we can natively interact with all these objects. So users can natively interact with all these objects without worrying about the source format. Okay, and this is where we designed Façades. We designed this like from the bottom up. So we looked and analyzed like as a kind of an ontology engineering piece of work. We look at the various different objects, and we made an abstraction that was capable of representing all of these objects as a graphs. The main native components, what we call the Façades components, are containers, slots, values, and types. Essentially, it's a list of lists, and we reuse native computer science patterns such as the sequencing and the maps. Okay, key value pairs, sequences, types, and values. And the idea is that we can apply this thing, applying the minimal possible ontological commitment. So we want to translate the objects as is, so that we can possibly even do the reverse with our lossless two-way conversions. Okay. For example, in the case of JSON, which is our most common example, I have a number of backup slides for other formats, if this is useful later for the discussion. So in this example, we have a list of two objects, and then key values for each one of them. Some of these values are lists themselves. So you can see by only using RDF type and RDF container membership properties and plain predicates, we can project the same object into an RDF graph, so that we can query it in SPARQL. How do we do it? Again, we try to do the minimal possible engineering additions, and we basically override the service clause. So we design a new protocol that in this is called SPARQL Anything, and from this protocol you essentially can connect to a Façades resource and query it as if it is a knowledge graph, all within standard SPARQL. So as you can see, just to give a bit of an illustration of how mappings go. So you have a select phase that is in the service clause, where you point at the JSON objects that we've seen before. And then we can do some transformation. For example, we build and mint our URI, and then we project all these values into a schema.org RDF snippet. Okay, so basic graph patterns, and SPARQL operators are all the ingredients we need to design our mappings. So we apply this notion to an open source tool and project, SPARQL Anything. This is originally developed and deployed in Java. There is also a Python extension wrapper that allows to use it through, for example, through Python code, through Python notebooks. It supports a good variety of format, from XML files to BibTeX or even PowerPoint presentations. Allows to operate with the file system, to process inline content. This is quite a good variety of functionalities, including HTTP, web APIs, and so forth. We had a good reception from we believe from the knowledge graph practitioner communities, and we have a growing community around this open source project. Okay, the most recent versions from July, when we have also a few new features like streaming construct queries, so that we can minimize the memory footprint and reuse queries, connect to Amazon S3 sources, and so forth. Okay, so going back to this idea of like what a mapping is in data integration, we can remap somehow what we did, in terms of design. So we have a selection part, and we have a target part, and we have a transformation. So the assumption that the format is not important has a big impact, we believe, in the way we design a data integration system. So the fact to have an homogeneous language to do all this work, I think we believe is one of the strongest selling point of the approach. This is one way we can compare SPARQL Anything and Façades to alternative approaches for knowledge graph constructions. And you can see from this table that we inherit a lot from a few other approaches, like the direct mapping one. So the fact that we map meta models. So we provide a direct access, similar to R2RML. SPARQL, we clearly inherit the way we build the knowledge graphs, the construct and the SPARQL. But what we do essentially is we design a meta model mapping of the facade, and then assume that the mapping from the facade to the various formats is something that a software engineer can do once and for all. Okay, so that the knowledge engineer can take care of the semantics and the remodeling and all the funny things that we want to take care of. Okay, and one of the things that are important to say is that we studied this thing theoretically, and that the facade is sufficient to map and represent any format representable in a BNF grammar, including like in addition to, for example, the relational model. Okay. Of course, the design decisions bring also features that can be seen as limitations. For example, SPARQL may not be the best language for everybody and everyone. Sometimes transformations can be very complex. I have a few examples later if we want to discuss them. But the fact that it's very powerful at the same time, things can become a bit harder to manage if you have very complex pipelines. Okay, the facade itself is very intuitive to some, less intuitive to others. The good thing that I like to say is that it opens up the opportunity for exploration before inspection, so we can make a query to a source without even having to open the file. Okay, so if we have a knowledge engineering skills, we can quite doing some like exploration of the source, but at the same time, others may find it harder to like, for example, deal with lists in RDF. Okay. Implementations limitations, we don't have the relational databases yet. Performance, so far the main query execution method is full materialization. So we build a full graph and then we execute the query. This may work in many cases, and actually works in many cases, but not in all of them. And so, for example, working and studying on how to make these queries more performant is an important research direction. Okay. The mapping itself is a query, which may not be the best object to manage, especially if you want to partition these mappings, you want to reuse these mappings. So this may not be fitting all workflows. And last but not least is that there is no standard yet. So implementers have to kind of make their own decisions or copy what we have done with SPARQL Anything. So in the last year, we focused a bit on this aspect of full materialization, and we tried to kind of start studying about a theory on how Façades queries can be executed. Okay. So the question for us was, okay, but what these queries look like? What are the peculiarities of or the specificities of Façades graphs, and how we can exploit them to improve query execution? Okay. Clearly, memory-aware optimization that we already performed, like triple filtering, are very good at reducing the amount of memory that is required to load the graph. You don't basically, essentially, you don't triplify the entire graph. You only triplify the part of the graph that is mentioned in the basic graph pattern. This is good, but it's not a full solution. If you do a kind of an SPO, let's say, subject predicate object query on a very large CSV, you will end up to hit memory limits. You will have an out-of-memory error, okay? Because the system will load the entire data in memory. There are strategies like slicing that we we have employed, so you can partition the source, doesn't allow to do the full query. In other terms, there is an open problem on execution. Okay, so we started thinking about that, and we first wanted to we started working on a theory on Façades basic graph pattern queries, in particularly first focusing on satisfiability of basic graph patterns. So which are the queries that can match at all against any possible Façades resource? So we studied the properties of the Façades meta model and the properties of basic graph patterns, and designed an algorithm to decide whether, given any basic graph pattern, whether it would, for example, give a solution to a possible Façades resource. So in other terms, because those formats and the nature of the Façades, there are some basic graph patterns that cannot have a solution. For example, recursions. So if you can have recursion in basic graph patterns, because you cannot have recursion in Façades graphs. Façades graphs are trees, are directed, acyclic. They have all these properties. So we can analyze basic graph patterns to make this decision. And we also studied this problem and found out that this is not a difficult one. So this problem is decidable in a polynomial time in the size of the pattern. Okay, so we can, in addition, we can generate all possible basic graph patterns that are annotated on all possible shapes that a Façades resource can have. And this is a very recent work that will be published on transactional graph data and knowledge, a special issue, I guess, in the next few months. And moving forward on that, again, this hasn't been published yet, so this is something we are working right now, but we have some results, so I wanted to mention it here. So we asked the question whether these queries, which kind of queries can be executed with very minimal memory footprint. And we found out that we can define a subset of these basic graph patterns that are satisfiable against Façades graphs, and that can also be executed with minimal memory footprint. So we managed to design an algorithm to identify those patterns. And we also made an analysis, including, we made an algorithm, of course, to execute this special type of queries with very minimal memory footprint. And we also analyzed the existing Façades queries. Essentially, we built a data set of all SPARQL Anything queries from GitHub. There are about more than 1,300 queries, a basic graph pattern extracted from about 450 queries. And we have seen that most of them are bounded memory admissible. So most of those, in other words, the bet is that in many cases, graph patterns used to construct knowledge graphs from Façades resources may not require excessive memory footprint. Okay, so there is a good chance that if we go ahead with this in this direction, we can provide a solution to perform Façades queries for many cases that are also memory efficient. Okay, this is a bit of a summary of number of evaluations against several different perspectives that we collected from the first paper at Semantics in 2021 until the work we are doing today. But essentially, as a recap, so from a theoretical point of view, any format expressed in a BNF grammar maps into a facade. So does the relational model, and the conversion is lossless. So we can really see anything as if it was an RDF graph. The satisfiability of basic graph patterns for Façades is decidable in polynomial time in the size of the pattern. We also looked a bit into usability, and for example, we measured how complex and difficult it is to represent mappings. And here we used a proxy that is quite a robust one in cognitive, like load research. And essentially, we counted how many tokens are needed to express the pattern. And we have seen that generally you need less tokens to express a mapping in Façades. We have done a few surveys about especially targeting knowledge graph engineers, so people that are proficient in SPARQL. So this success is bound to the fact that we are targeting a specific community. And then the performance part, this is about full materialization. So full materialization is comparable to alternative approach in terms of performance and efficiency for many small items. And things become very large. Clearly, the story is different. Trouble filtering is very effective. But we have seen that materialization will fail when, for example, let's see, on 4 GB, we have 8-10 million triples to be loaded in memory. Okay, so when this is the case, you need a different approach, and we try to do that, starting this research on bounded memory admissible basic graph patterns. Okay, the other aspect that I think is nice to mention is the one of that looks at software engineers. Okay, so we want to simplify things for the SPARQL users, for the user. What about having to deal with the machinery behind it? Okay, so how complex it is to develop and maintain a Façades execution engine. And this was the first analysis in 2021. And now clearly the number of lines of Java code has changed. So I'm not sure if this is still true today. But again, the story here is that this is certainly doable with normal software engineering skills. Okay, you don't need to be a superhero to write a simple Façades engine. Okay. So there are other research directions and things that we haven't done, but we will be very happy to do in the future, or I will be super happy if anybody would like to look into these problems. Clearly, expanding the number and the types of SPARQL queries that can be analyzed in terms of, like, for example, admissibility, for example, covering other operator in SPARQL, using format-specific aspects to improve the efficiency of the execution, and look at other workflows. For example, we can have a software that indexes Façades resources for efficient execution. There we can split the evaluation in intermediate steps. We can reuse and cache mappings and query solutions. So we can do other things, including like expanding the implementation to cover relational databases and databases in general, because so far we don't have that. However, we've done some progress around standardization. Last year, we launched the W3C Data Façade community group with a number of practitioners that joined us with enthusiasm from the beginning, and we are very, very, very grateful about that. And the objective is clearly to standardize the approach, the meta model, and to have a workflow to define standard specifications for all the formats covered by SPARQL Anything, and maybe for new ones, to specify the way the Façade can be used in SPARQL, and to build an ecosystem that is interoperable beyond SPARQL Anything. So not only SPARQL Anything, but also other implementations, so that we can have an open standard alongside that. So as I said, we launched last year. We have started to develop drafts for a number of specifications. We are going to continue with that in the next few months. Please, if you are interested in that, join the group, attend the meeting, or send us an email. We want to really hear your stories about your problems and also your use cases. We want to have a specification, first version of the specification for comments by the end of the year. This is a good challenge for us, and hopefully really we'll manage to do that. Okay. I'd like to want to report about some feedback on early adoption that we collected during last year. And I hope I am not, I have time, I hope. So we, as I said, we invited early adopters and speakers to tell us their experiences on our community group meetings, their experience from teaching, from applications and deployments in EU public procurement, in railway infrastructures, and also implementations of in proprietary software houses like Data Tree House and Triply. So this has been really, really good, inspiring, and we are also they also had an impact on the way we are developing the specifications, and we are improving a lot of things thanks to this feedback. But essentially, the stories span around the benefit of keeping the extraction separate from the interpretation. Okay, so one thing we didn't really think of with Luigi originally was the fact that this approach may change the way the whole workflow was managed. Okay, a lot of use cases want to have a clear mirror of the source before separated from the transformation, and not losing it every time. For example, you run the mapping, so you could analyze step by step what was going on. So this load first, refine afterwards seem to be a good approach. And also the fact that everything is done with standard SPARQL is a good thing, both for teaching, because if you teach knowledge graph management, you don't need to teach another language. You can make your students work directly with SPARQL to load and transform the data, but also for the production team. So if you have a production team, everything, the expertise required becomes consistent. Okay. And also the fact that the materialization was a barrier, it's not very common, actually. In many cases, that the full materialization is good enough. Most of the cases have small files anyway, and if they are large files, slicing works very well, because you usually want to apply transformation at the row level. You rarely want to join different rows in a CSV, right? So slicing sources works very well. Anyway, but this is good news. So I'm going to finish now and inviting you all to the tutorial we are presenting at ISWC together with Luigi Esprino, Martin Harmelen, Matthias van den Heuvel, Ryan Shaw, and Ivo Velichkov, which are among the most active members of the community group. And we are going to do a bit of hands-on on SPARQL Anything and Façades, but also listening to their stories about applying this technology in production, and also listen hopefully to the stories of the attendees. We will have a clinic where we will listen to problems in relation to knowledge graph and data integration. Okay, I think this is all. I want to leave you with a few credits of all the people that have surrounded this work so far, especially Luigi Esprino, which is my co-author and co-creator for what concerns everything that I said today. So a big thank you to Luigi and everybody else here. And then I'm happy to answer your questions.